This simple graph shown here, or relation represented by this digraph, is even, and we want to find the power of this, or graph powers, for this relation shown here, g squared, g cubed, and g to the power 4. So the first thing to recall is, what do we mean by the graph powers? It means basically the composition of relation, or composition of graph, or cascade of graph. So that means if you think of graph as a function that maps 1 to 2, and then if you want to continue, 2 to 1, and so on and so forth, it's as if you start with selecting one node, and you would use the graph digraph provided in terms of what is mapped to what, and you get to an output. For example, 1 comes in, it maps to 2, so 2 comes out. Then this 2 comes out, you're now feeding it one more time to the same graph or relation, so it becomes another graph in series. So this is what we refer to as the cascade of the graph, and you would say this way, you would say this whole thing is what we represent as GOG, or composition of relation or graph, which is symbolically shown as g squared. If you want to make and form or construct, say, g cube, you put another g cube, you put another g in cascade, in series, and that means the output is again fed to the input of the relation one more time. In this case, you would refer to the whole thing as g cube. So it would be g cube. There you go. This whole thing is now g cube. And you would say g cube is, of course, whatever you had, which was a g squared, now OG. So you are putting another, you're inserting another copy of the graph or relation as a third cascade to the whole thing. So recalling the cascade, what comes on the right side, like this one, should appear first in the series, and then the next one here on the left side of the composition operation should come as the last insert in the series. So that's how you graphically show g squared in the formation of g cube. Of course, if you want to form, say, g to the power 4, you do the same thing. You insert another g in series, so it would be the fourth one, and you would say GOG cube. So that's just the procedure. Now that we know what's happening, let's go to the process. So at the beginning of this cascade, you come in, say at node 1, 1 is mapped to 2, so the best way to remember this is graph G. Let's say, let's refer to this as relation G, it's okay. So we are saying 1 maps via graph G to 2, okay, great. So that's the operation here, but then 2 is either mapped to 1 or mapped to 3. So you can say and 2 is mapped via graph G to 1, or you can say, 2 is mapped via graph G to 3. Okay, as you can see easily, the consequence is 1 effectively is mapped to 1 via the 2 cascade here, because it goes to 2, then 2 goes back to 1, or 1 goes to 2 and 2 goes back to 3. So the consequence is you end up with 1 via g squared maps to 1, and 1 via g squared maps to 3. Okay, great. So if I'm supposed to show the graph for, say, g squared, I would put it this way. I would have, let me show it here. Okay, so I would have g squared, and then I would have 1. Maybe the best thing to do is just go a little bit down. So I would have 1, I would have 2, and then 3. Sorry, that's 4. So this is 3. And finally, I have 4. Okay, and what else do I have? I found 1 on g squared. If this is for g squared, I see 1, 1. So it means a self loop on 1. And I see 1, 3. So it means 1 goes to 3. Okay, great. What else do I have? Now, I just investigated coming in hot at 1. So what if I just come in um, at 2 at the very beginning of the system? So you come in at 2, 2 is mapped to 1 via G. And remember, if you're doing G squared, we are doing GOG. So 2 is mapped to 1 via G. Okay, 2 is mapped to 1 via G. And then you will see that again, 1 is mapped back to 2 via G, second G. There is no other choice for you. So, and 1 is mapped back to 2. So effectively, that's one choice. The other choice is 2 come in at the very beginning is mapped to 3. And the only other way via the second G is 3 goes back to 1. So 2 is mapped via G to 3. And the only other option is 3 is mapped via G to 1. So from here, you conclude that 2 goes to 2 via G squared. And you see that 2 goes to 1 via G squared. Okay, so that means we have a 2, 2 on G squared means you have a self loop here. And 2 to 1 means we have this guy. Okay, there is no other choice we have here. Now let's assume at the beginning of system we're gonna enter at node 3. 3 can only goes to 1 and via the first G, and then via the second G you can only go 1 to 2. So what you're saying is you are saying I'm just thinking where to write. So you're saying, um, you're saying that if we come in 3, then 3 is mapped via G to 1. So if we come 3, then G maps it to 1. And at the same time, 1 is mapped via G to 2. So effectively, and that's the only option for 3. So effectively, 3 is mapped to via G squared, is mapped to, 3 is mapped to 2. Okay, so 3 goes back to 2. And last one, 4, if we come in here at 4, 4 is mapped to 3. So if we come in at 4, 4 is mapped to 3 via G. And 3 is the only option for 3 for via the second G is 3 is mapped to 1. So 3 is mapped to 1. So in conclusion, you can see that 4 is mapped to 1 via G squared. Okay, so this is the graph for G squared. Now, if we want to go G cube, we have to consider this. Let me change the color so that there is no confusion what I'm talking about. So this would be the situation with G squared. This one, G cube. So first G squared come in, which we already have it. And then after that, the output of G squared that is shown here goes to G. So we have to come to this one that is shown. So what I'm trying to show you guys here is we have G cube, and then naturally we have again node 1, node 2, node 3, and then we have node 4. So what we have for G cube is we come in 1, 1 is mapped to 1 via G cube. That's why we enter to G cube, and then output of G cube is mapped to is forced as is fed to a G. So 1 comes to 1, 1 comes in, 1 goes out, but then here via the third G, 1 can only go to 2. So therefore in G cube, 1 goes to 2 from the very input to the very output. I'm just doing it quickly, but if you want to write it, it's as if you're saying 1 is mapped to 1 via G squared, but then that 1 now is only mapped to 2 via the third G. So as a result, 1 is mapped to 2 via g cube. Now, any other options we have? We enter 1. The other choice is we don't go back to 1. Via g squared, we go to 3. Okay, if we go to 3, so 1 via g squared goes to 3. And now via the g, 3 can only go back to 1. So 3 via g goes back to 1. So therefore, 1 goes to 1 via g cube. So we should have a self loop here. Okay, if we come in, and that's the only option we have for 1 when we enter g squared. Now, if we enter g squared here via node 2, 2 can be, we have a self loop on 2. So what we are saying is 2 via g squared has a self loop that maps it to 2. But then we are here with 2 coming out. So 2 goes in, 2 comes out, and that is the input to g. So 2 input to g can go to 1. So, and 2 via g go to 1. So therefore, one choice is we get 2 to 1. But then the other option is 2 via g can go to 3. So I have 2 via g goes to 3. As a result, 2 via g cube is mapped to 1. And also 2 via g cube is mapped to 3. So 2 is mapped to 1. 2 is mapped to 1. This is need correction here. So 2 is mapped to 1. And then we are saying 2 is mapped to 3. So 2 is mapped to 3. Okay, we are done with 2. Imagine that now, because we investigated, let's see if you're done with 2. We said 2 comes to g squared, 2 goes out, but then 2 goes out, enters g, so can go to 1, can go to 3, which we found the answer. But then the other choice is 2 comes in and 2 goes to 1 via g squared. And so the other choice that I missed here is 2 comes via g squared, enters g squared, and then goes to 1, and then 1 via g goes back to 2. So as a result, we know that 2 g cube 2. So there should be a self loop on 2. Okay, so that's done with 2. But then let's assume that we enter 3 for g squared. If 3 comes in, we can only go to 2 via g squared. So I'm going to write it here, 2. So 2 comes into g squared. 3 comes in g squared. So as a result, we can only get 2. There is no other choice. Now we get 2. 2 enters g, and then we can go to 3. Or we can go to 1. That's it. We don't have any other choice. So that means 3 via g cube is mapped to 3. And that means 3 via g cube is mapped to 1. So there should be a self loop here, and there should be this connection as well. There should be this connection as well. Okay, that's the only choice we have. Now regarding 4, if 4 comes in to input here and enter g squared, then 4 is mapped to 1. So we can see that 4 via g squared is mapped to 1. And then that 1 enters g, and you can see there is only one choice. 1 is mapped to 2. So, and 1 via g is mapped to 2. Therefore, we can say 4 via g cube is mapped to 2. So that's the only choice we have. I'm going to show it with different color because it's, or maybe just a little bit different so that it's visible. So, okay. So it is this connection. It is this connection. that concludes our conversation about g cubed. Now the last one is g to the power 4. You can see it become a little bit busy because we enter this busy node, and then we're supposed to just route the output to g, because g is showing up in the formation of the g to the power 4. You have this g cube already formed, and then you put another g in series, the fourth one. So you come in at the input of g cube relation or graph, you go out from it, and then you enter another g. So in this case, 1 comes in, and you can see either 1 goes out or 2 goes out. If 1 goes out, you have only 2 options. So let me just use different color to just finalize it. So 1 comes into g cube. Let me show it here. So 1 comes into g cube, and if 1 comes in, then 1 goes out, or if 1 come in, then as you can see, 2 goes out. These are the only options we have. If 1 goes out, then via G, 1 can be mapped back to 2. So 1 via G is 2. Therefore, 1 via G4 is mapped to 2. And if 1 is mapped to 2 via g cube, then 2 is either mapped to 1 or to 3. So, and 2 is mapped to 1 via g, or 2 is mapped to 3 via g. So as a result, 1 is related to 1 via g4, and 1 is related to 3 via G4. So in the network for G4, we should have um, these. Let me make sure that I'm not missing something. We should have these connections. So we should have a self loop on 1. We should have a connection from 1 to 2 and from 1 to 3. Okay, so another color just to make it easier. Now, if 2 comes in, we can go to 2, we can go to 1, we can go to 3. So it become busy. 2 comes in, we go to 2, then 2 go to 1 to go to 3. So 2 can go to 1, and then 2 can go to 3. I'm just doing it quickly. And then if 2 comes in, we go to 1, then 1 can go back to 2, so that means there's a self loop on 2. And if 2 comes in, then assuming that we go to say 3, then 3 can only go to 1. So again, 2 to 1, 2 to 1 is a choice that I have already shown. So these are the consequence. If using different color, so if now we come in 3 on in G as the input to the G cube, then the only option we have is we go to 1, and then 1 enters G, and we get to 2. So 3 get back to 2. That looks like the only option. Of course, we have a self loop on 3 as well. So 3 goes to 1, 1 goes to 2, you're done. 3 goes to 3, and 3 goes to 1. So 3 goes to 1. That's another, that's also another one that we need to be careful. Okay, finally, 4 comes in to G cube, we get 2. Okay, we get 2, and then 2 can go to 1, can go to 3. So that means 4 can go to 1, 4 can go to 3. That's it. So of course, what we did here, sort of in a verbose fashion or intuitive fashion, can be done with simple matrix multiplication if you write the matrix representation of the graph G. If you are interested to do that, just recall that matrix representation for graph G is just since you have 4 vertices, 1, 2, 3, 4 is a 4 by 4 matrix, and is as simple as this. So it's going to be a 4 by 4 matrix, and it is so node 1, 2, 3, 4, and then you have node 1, 2, 3, 4, and then you just list the connection. There is no on graph G as shown here. There is no connection from 1 to 1, so nothing. From 1 to 2, there is one connection, one edge. 2 to and 1 to 3, there is nothing. 1 to 4, there is nothing. 2 to 1, as you can see, 2 to 1, there is one connection. 2 to 2, there is nothing. 2 to 3, there is one connection. 2 to 4, there is no connection or edge. 3 to 1, there is. That's the 3 to 2, there is not. 3 to 3, there is not. 3 to 4, there is not. 4, 4 has only a connection on graph G to 3. So 0, 0, and then 1, and then 0. So you can see that in the matrix representation of graph G as expected, we only have 5 non-zero value corresponding to the 5 red edges, 1, 1, 1, 1, 1. And then when you want to form matrix representation for graph G squared, then you have to do matrix multiplication. So you utilize that property to come up with the connections. With that in mind, that's an exercise for another video. I just wanted to make to just go through this exercise to find the powers of a graph and remind that the power of a graph is nothing, or relation is nothing but cascading of the relation in composition of relation as illustrated here. I hope that this video is helpful.